the one that you are familiar with by now is just the two penetrometers, the SPT and the CPT, right? The standard penetration test and the cone penetration test. So if you look on page 14, the bearing capacity equation is just the area of the shaft multiplied the skin friction on the shaft plus the area of the tip, right, at the end of your pile multiplied by the ultimate bearing capacity that acts on the tip of the pile. So if you recall, just to remind ourselves again, right, I don't really have to do this, but students need to reminding. If this is the pile, so if I stick it into the, say, the sand, all right, in this case, we're talking about the sand. So we have shaft friction around it, friction around the shaft. And then at the bottom here is the tip. So it's just the skin friction, which is a stress, right? You multiply by the surface area and the tip resistance here at the bottom here, and you multiply by the area of the tip. This is in relation, of course, to the load that you apply at the top, all right? So you apply the load to the top, so there is a friction that reacts against the load, and the tip also react against it. So that's why you get that equation on page 14. Now, if at the bottom here, if it is circular, like this one here, circular, right? So then the shaft friction would just be, the surface area of the shaft friction would just be pi BD multiplied by F sub S, right? And A tip multiplied by Q out. A tip, if the circular again, then it's just pi multiplied by the diameter squared of the shaft by 4, right? And you have been going through some of those examples, all right, with me, and then you have been doing some of the work. So on that assumption, on the assumption that you're familiar with, by now you should be familiar with this formula, right? So the two penetrometers that we're dealing with, right, are CPT and SPT. So if we are talking about CPT, yeah, there are two parameters that we obtain from the cone penetration test. This is just reminding you again the site investigation topic that we did before, right? So there is the if I have a penetrometer, this is my penetrometer, so I have F sub C and Q sub C. Now F sub C is the shaft skin friction of the penetrometer. So F, the word C is just the symbol for the cone, and then Q sub C is the tip of the cone. All right, so those are the two that give you where the ultimate bearing capacity when you penetrate the penetrometer into the sand. All right, so now the question is just to use what are the empirical equations that people supply with, and then into the equation of that Q out equal to pi BD F sub S multiplied by A tip Q out. All right. So the first one here, you get the ultimate bearing capacity Q out. Yeah, the ultimate bearing capacity is equal to Q sub C. Q sub C again is the tip of the penetrometer, the bearing capacity at the tip of the penetrometer. So they are saying to you, if I have a penetrometer, I stick it into this sand, whatever the tip resistance that I get from the sand, I can just substitute it into my equation for the pile. So it's the same, right? That's one of the empirical equations. So next page is on page 15, is the one by Mayhof, and he says to you that actually he suggests also that there is a relationship between the tip of the ultimate bearing capacity of the cone and the SPT. In other words, if you do the CPT test with depth, right? You take the Q sub C at certain specified depth. It can also be related to the SPT. Now in SPT, we said to ourselves that the value that we obtain is N. N is the penetration resistance, okay, of the soil, and that N all right, if you multiply by 4 from the SPT is equal to Q sub C. So, and you can change it to Q sub C divided by 4, or you can have Q sub C if you do test for with respect to the CPT. So you have Q sub C result, then you just multiply that by 4, right? Sorry, you divide that by 4, you get N. If you do SPT test, you multiply by 4 and then you get the Q sub C. All right? So that's just a relationship that you might find useful. If you recall in my example for the SPT previously that we did, right? I drew the CPT with depth, all right? And I even asked you for the homework, it was 8.8B if I recall correctly. And then I said you must do it like my example, all right? Not any other way, not like Rick's book, I said. So there was Q sub C with depth. So if I use the same correlation, all right, I can also have SPT with depth. This is just to remind you that because we do these two penetrometers in sand cohesionless material, so you know, if I get one result, I can also draw for the other result, because I think by now you realize SPT is quite versatile, and therefore you like to have both result if it is possible. All right, you may not use it, but it's good to know that you know you can have that relationship. Now the other one is that, you know, just now we talked, the other component was the shaft friction of the pile multiplied by the surface area, and the first part was the tip resistance multiplied by the area of the pile. All right, here's my pile, here's my penetrometer. Here are the things that we're talking about. So whatever comes out of the penetrometer at the tip is the same as the pile. Now the other part is the shaft. The relationship of the shaft, all right, the first relationship that is given here is this F sub S, all right. The F sub S is QC bar over 200. Now, if you only have the QC, right, at each depth as you go down, all right, so you take the average of the depth over the specified pile, all right, because here's my penetrometer. At every depth, I take the tip resistance Q sub C. Another one, right? So if my pile is here, right, so then I can have all these Q sub C. I average them, okay, and I divide it by 200, and I say that's the shaft friction for the pile multiplied in the area. All right, so that's one. The other one, in other words, if you take the shaft friction from the penetrometer, is equal to 2 times the F sub C, which is the cone penetrometer. Pile F sub S equals to 2 times F sub C if you ever have the shaft friction of the penetrometer. So the first one, you can have Q sub C bar average divided by 200. The second one, if you have all this F sub C, the shaft friction from the penetrometer, you can take all of this value, multiply by 2, use it for the pile. Okay? So those are the empirical equation. Now for the SPT, you use this equation here, 100, yeah, in bracket multiplied by 4 N A tip plus N bar A sub S over 50 kilometer. N bar is the average value of the SPT over the pile depth. All right, you get your SPT value from your SI. Now, if you have small displacement pile, the Q out is 100 multiplied by 4 N A tip plus N bar multiplied by AS, but now you divide by A sub S. The N bar multiplied by AS, whether you divide by 50 or divide by 100, that is the shaft friction, okay, shaft friction for the pile. And then here, the shaft friction for the pile is equal to the shaft friction of the cone of the SPT. All right. So all this empirical correlation, and then how do we relate the shaft friction and the tip resistance from the result of the SPT and from the result of the CPT. So now we just need to see an example to see how it is being applied. All right. The first example here is example 8.8 on page 308. All right, 308. Now I have 54 people. 4 people are missing. Arman, are you here? Hello, Arman. Okay. You want to like ask from them, Google the attendance, please. All right. And then if they want to drop off from from the class, it's okay. But then, right, they already know what homework to do to send. But I may ask for you for another homework, right? Depending on how we get by. If that is a good way. Syakila, Nabila. Syakila dah muncul, sir. What happened to you, Syakila? Okay, Akbal, you have sent the attendance. Good for you. Thanks very much. Syakila, what happened to you? Sakit ke? Balik kampung ke? Connectivity tak ada ke? Siap je, sir. Then what happened to you? Baru ada connection. Ya Allah. Ni kat Melaka ke kat mana ni? Kita balik kampung tempat lain pula. Connection dah hilang balik lah nanti. Oh Syakila, are you in a shopping mall? Aja ahaha. Aja ha. Ha. Terima tu terima. Aja hahaha. Hafizi balik rumah husband pun. Ha? Syakila dah kahwin je? Aduh. Okay. Syakila. I'm just worried. Alamak. Dekat awak balik rumah husband. Ni Mano Hafizi ni joking ke? Syakila, you're not married, are you? Alright, I am in the example. You haven't lost much. So I'm on example 308. Alright. On example on page 308. I don't know why I put page 335. I think it's because I was using another edition then. Liana, yes sir. PG likes to joke. Yeah. Must be a boring subject. Find foundation engineering, or he rather find it easy. Alright. Kalau tidak, dia kena tidur. Okay, look, I am on the example, page 308. Go to page 308. Alright. Example 8.8. A straight footing is to be designed to carry a load of 800 kilonewton per meter at a depth of 0.7 meter in a gravelly sand. Alright. The appropriate year, example 8. It says example 8.8, page 300 and, page 335 kot, Let me see. Example 8.8. I must have been like asleep. Example 8.8. Right. Example 8.8 is page 348. All right. Thanks very much, Amy. Actually, I wrote 348, but I read it as 308. Sorry, guys. Apa tu? Ain, are you there yet? Page 348. Example 8.8. Okay, fine. I assume yes, sir, means that you are on page. Okay, fine. Sorry, guys. All right. So I put the blind down so the gelap sikit hari ni. All right. You may not see me as gelap, but it's a bit dark in the room today. Okay, sorry, guys. So example 8.8. Ya Allah, apalah pun yang asyik nak jatuh. Now I don't know what happened here. At least Amy ada sense of humor. Fazli pun ada sense of humor. Tak lah, less friction Fazli. Yeah, I don't know. Ini I copied Shakila style. She put the phone on the laptop, right? So kan itu hari tak ada what the heck do we call it? The tripod. Kan Syasha nak ajak saya pergi belilah semua kan. Lepas tu dia jadi macam ni. Alright. So betul Hafizi. Behave. Fine. Alright. Example 8.8. Focus. Results of cone penetration test at a particular site are shown in figure 8.25. See, you see that figure there, 8.25. That's how the SPT result, the CPT result with depth is. Remember all that curve? All right. Now, on the basis of this result, to what minimum depth should a 600 millimeter diameter concrete pile, the pile has a diameter of 600 millimeter, be driven in the dense sand if the shear zones are to be fully developed? All right, what load could the pile then support if a load factor of 2.5 was specified? Load factor of 2.5 is, if I hadn't explained it to you previously, they use this word load factor, what you and I know as the factor of safety, all right? But they just want to be specific. It's the factor of safety you apply to the load, all right, that you calculate, all right? Now, if you look at that figure 8.25 on page 349, all right, you have Q sub C against depth, all right, cone penetration against depth. Now, you notice that there are two types of soil here. They actually explain to you that there is two types of soil. One, the upper layer is a loose uniform sand. The second layer is a dense, well-graded sand. Now, immediately you know if you have a well-graded sand as opposed to a poorly graded sand, this is from soil mechanics 1, you know that a well-graded sand would give you a denser material because the pores are being filled up by the smaller particles, right? So they have less pores. So you get a dense, well-graded sand. If you then get the dense, well-graded sand, you also immediately say to yourself in your head that it is hard to penetrate. In other words, it gives you more strength. All right. If you recall, a lot of times I try to explain to you the things that you find in your house. Say in your kitchen you have rice, right? You have loose rice and you have dense rice, all right? One which is well compacted and one which is loose. So the dense, well compacted rice, right? You can't even put your finger in it. If you try to push it in, right? Sometimes your finger might be feeling painful, right? As opposed to the loose rice. Okay, so that gives you an indication of the strength. So why, when they talk about this question, they are referring to the need for you to try to get your pile in the dense sand so that you get more of the bearing capacity and the shaft friction as opposed to the loose uniform sand, right? In the loose uniform sand, you may not have the shaft friction and also the kick resistance. So you might not have sufficient total bearing capacity, all right, to carry the load. Plus the fact that they want it to be like 2.5 factor of safety. So they are referring to this procedure by a person called De Beer. All right, I'm not going to talk a lot about the procedure here. I'm going to assume you're going to read the procedure in the book, but I'm going to refer to it when I do this example with you. All right. So this procedure is on page, the Beer procedure is on page 337. You might want to have a quick flip over so that then you can, you know, when I refer to it, you can refer to it. Then you can find the time to read outside of my time with you. Okay, so page 337, that's the figure, all right, and this procedure. So you might need to flip like that or occasionally, like what I will do, all right. So the base procedure will be used, that's on page 337. Then it says by inspection of figure 8.25, the cone resistance is fully developed over a depth Y sub C of 0.3 meter. Now you look at this, figure 8.25, right? So like I said, there are two layers there. One is the loose uniform sand, the other is the dense sand, all right? So the one here that is the loose sand. So you just draw a straight line through it, take an average value. Then the same with the dense sand, the one in the bottom. Now in between the very loose sand and the dense sand here, there is this transition zone. All right, transition zone whereby the loose sand, right, changes over to the finally the value of a dense sand. All right, so BC is of that 0.3 meter. Are we okay, guys? BC is 0.3 meter. How do you get that value? You just like, look at by eye, you draw a straight line, and in between you also draw a straight line. So there are like 3 different slopes there. Okay? I need you to understand that, because otherwise you won't know what I'm talking about. While I get a drink of water here. Guys, respond. Okay, Anis kata, lama tak jumpa Anis. Khabar Anis? Alright, Ain Fitra pun kata, Ain pun kata okay. Alright, so now, then it says, okay, hence the base resistance of the pile will be fully developed over a depth of YP. Now this depth YP ni, it's an equation which is given on page 337. So if I flip to page 337 again, all right, it is an equation that is like on the first paragraph of page 337, I believe. Where is the equation? YP is equal to N multiplied by YC. Can you get that? YP is equal to N multiplied by YC. All right. It's on the, if I, on page 337, if I were to read the lines from the bottom, 1, 2, 3, 4, 5, 6 from the bottom. The 6th line from the bottom, or rather the 7th line from the bottom. The 7th line from the bottom says, however, for a pile having a diameter or equivalent diameter n times that of the cone, the penetration of y sub p equal to n sub ny sub c into the dense stratum would be required before the maximum base resistance was obtained. Okay, and then it said the line with BD would then represent the corresponding increase in resistance during penetration of the pile. All right, guys, you know that you have to read page 337, okay, to understand more. Otherwise, I'm referring to them, all right, where these things are happening. The assumption is you read this. So YP, the depth, all right, YP is just Y sub C, which we have calculated to be 0.3 by eye or by inspection, and then multiply by N. N is a ratio of the pile diameter with respect to the cone diameter. So the pile diameter was 0.6 meter, 600 millimeter, all right, in the equation. And then the diameter of the cone is 36 millimeter. How do I know that? That's the standard SPT cone penetrometer. All right, that's a 6 millimeter. Also, again, you will find that in on the page about the CPT or the cone penetrometer. All right. Okay, so that's why you get it to be Y sub P to be 5 meters. So in other words, the pile should be driven 5 meters into the dense sand. Okay, for the full load to be mobilized. In other words, you will get the maximum tip resistance and you get the maximum shaft friction, all right, in the dense sand. So 5 meters from point B, all right. So total length will therefore be, well, AB is 7 meters, then D is 5 meters. That's the length of the pile that you need to put it in, all right? So total length of 12 meters. Now, the increase in resistance during driving of the pile is represented by BD in figure 8.25. So now that you know where the pile should be resting in the dense stratum, you then connect a line between B and D. This B and D connecting is in accordance to the Beer's procedure. This is the recommended procedure, which is found on page 337. All right, so I'm just merely repeating the procedure in the example. Hopefully, you will read the theory. All right, and then you will see, you will understand more. Why didn't I talk about the theory? Because I noticed that when I talk examples and give you the theory and apply the theory, you follow the explanation much better. And then you also see the importance of reading the theory, right? Sometimes I just give you the theory, then, immediately, and then I go into example, you almost forgot the theory that I just explained, all right? So now I'm just using a different way of doing it. All right, so then the ultimate value of the base resistance to be used in design is 8.6. This 8.6 meganewton per meter squared is the average between 3B above and B below the base of the pile. This value is less than the damage limit of 10 meganewton per meter squared. Again, on page 337, it will explain to you that in order for you to get the tip resistance, all right, the tip resistance of the for the pile, from the penetrometer result, you need to take it 3B above and 1B below. All right, and then you take that average value. So if you do that, 3B below at a depth of 12 meter, 3B above and 3B and 1B below, you get at 3B below is, 3B above, all right, you get it at about 8 point something, all right, and then 1B below, you get about what, 9 maybe. So that's why you get 8.6. All right. Okay, guys. See, when you don't respond to me, I don't know whether you're following me or not. All right. Okay. Azli kata okay tu okay lah tu. I try to follow. All right. Okay. All right. Then this value at the tip, according to the Beer on page 337, okay, on page 337 too, would be, the value should be less than 10 meganewton per meter square. All right. Why is that? They find out that you cannot get more than 10 meganewton per meter square. So you need to refer to page 237 for that. All right. Good, Iskandar, you are around. All right. Iskandar ni, he's smart. I believe he's smart. I don't know. Okay. But kadang-kadang tuang. All right. A bit playful maybe. Is that right? He's very amazing. Good. All right. Good. So kadang-kadang tuang, so sometimes can be a problem. All right. I'll talk about all these issues later if I have time today. All right. So the values of skin friction in the loose and dense sand are given by QC bar over 200. Well, a few minutes ago, this was what I said to you is Mayhof's expression, all right, empirical expression to determine the shaft friction. All right. Q sub C bar is the average cone penetration resistance in each case. So what you need to do is that you need to figure out the F sub S for the pile, the skin friction for the pile is from the Q sub C. In this case, the F sub C was not taken, right? So we only have the Q sub C. So from the Q sub C, we take the average value between the loose soil and also in the dense soil. There are two different values. The average value of the loose soil, because these are two different layers, right? The average value in the loose soil, then you divide it by 200. Then you take the average value in the dense soil, and then you divide it by 200. So that's how you get that 10 and 38 in the loose sand and the dense sand. Now, apply the equation in the general equation of Q sub U, Q sub ultimate or Q sub F, depending on what you want. ABQF right? Plus summation of ASFS. Why summation of ASFS? Because there are two layers. One is loose sand, the other is the dense sand, all right? So the tip resistance is area of the tip pi d squared, all right? The diameter pile is 0.6 pi d squared divided by 4. Then you have found the tip resistance 3B above and 1B below. That's 8.6 meganewton per meter squared. So they change it to kilonewton per meter squared. And then you multiply the shaft friction. Here's a pile, shaft friction in the loose sand, and then the shaft friction in the dense sand. So that's pi B, right? Pi B multiplied by the depth of the loose sand, 7 meters, and then you got that skin friction for the pile there to be 10, because you see QC bar divided by 200, the average is 10. And then in the dense sand, 5 meter deep, all right? And then for the skin friction to be 38, so you get 2921 kilonewton. So the allowable load, now the ultimate load, right, divided by the factor of safety for the load, which is 2.5, so you get 1168 kilonewton. Are we okay thus far? Yes? You know, ask me anything you like now. No? All right. I assume you get it. Now, if in real life, if you do not want to use the skin friction, right? Have you calculated all of this? It's not saying that there isn't the value is there. But if you ever decide, all right, not to use the values from the skin friction in the loose sand, you can disregard it if you like. All right, that's what he means by it should be acceptable, would be acceptable to disregard the skin friction in the loose sand. All right, but I wouldn't suggest you to start out your career doing that. Okay. Aduh, Amy tu dah marah tu. Sembang jap lagi Betul tu Amy. Okay, any question on example 8.8? You saw how this CPT is being applied now, right? Going once, going twice, going 3 times. So I assume no question. Okay, done. Now I'm moving on to negative skin friction, which is on page 16. Right? Page 16, negative skin friction. Okay, guys? Now, so I'll just read it. Negative skin friction, which is NSF. Acts on the pile when the soil surrounding the shaft move or settles relative to the pile. Typical cases. All right. Let me explain the phenomena first, all right? So the diagram there shows to you that I have my pile, okay? Pile is in soft clay and in dense sand. A few minutes ago when we was doing that CPT, we said to ourselves, it would be great to have the pile in the dense sand or in stiff clay. We have stiff clay because this would give us a higher bearing capacity, all right? So we stick it into the dense sand, and then we notice that there is a soft clay with this dense sand from the site investigation. All right. Now, after we have installed our piles, we build our house. In this case, it looks like a house to me, a single or double story house. All right. And then later on, we say to ourselves, you know what? We need to put some fill. Some extra soil on top of the clay because for whatever reason, maybe you don't like the color of the clay. All right, it's as simple as that. So you put some layer of soil, good soil, yeah, and then you call it a fill, and then you compact it, and then you leave it, right, for a while. Okay, and you haven't moved into your house yet. You're gonna move into your house at some point in time. Now, when you apply this additional stress to the clay, all right, the clay is, number one, you already know that it's soft, okay, soft clay. So you know that it's weak, all right. I'm saying to you, you know, because you've learned soil mechanics, right? You know, it could well be you don't know if you are buying the house and you don't have an engineering degree or you never learned soil mechanics. So I'm assuming that, you know, I'm talking this to a person who is familiar with soil mechanics, right? So when you put additional stress, right, to the clay, because now the clay, right, you know, has finished consolidation and everything, there is no more settlement, right, and construction is over. But now when you put the fill on top of the clay, so now you have additional stress on the clay. All right, this additional stress increases the pore water pressure in the clay. So now you have excess pore water pressure again. All right, this excess pore water pressure again has to be dissipated. Okay, and dissipation occurs through drainage. All right, okay, so it takes time. Drainage occurs. All right, but now when drainage occurs and the dissipation of this excess pressure occur with time, now the soil settle because the volume decreases. All right, now fine, you know, if it doesn't if the pill, right, just it goes down, right? But what happens is that you notice now when that soil goes down, it pulls the part of the pile in the clay. See, this is in the clay, right? Here's your surface, here's the part of pile in the clay. It pulls down the part in the soft clay. All right, but in a dense sense, it's the opposite because it's not going down there. You know, it's dense, it's strong, so nothing happens to it. So it is still in the direction it's supposed to be. Remind ourselves. Here's my pile. When I first draw the pile to you, right, a couple of pages back, right, I'm putting my load, right? This is nothing to think about negative. I'm just thinking normal. Here's the load from the column. All right, here's my surface. Here's my surface soil. Here's the load from the column. All right. I said to you, even a few minutes ago, I said to you, there is a resistance from the tip of the pile. Then there is a resistance from the friction because you're pushing it downward. All right. So the soil around it react. It's opposite to the load. So it's upwards along the skin friction. Both are upwards. Load is going downwards from the column. All right. In this direction, it is all positive. So now you look at this, the first picture here. All right, this picture here. All right. So I ask you, the reaction, the sharp friction reaction in the sand, in the dense sand. All right, the direction, is it positive or negative? Having explained to you a few minutes ago, if you what happens when I apply a load to my pile. So in the dense sand, is it positive or negative? Just say anything you want, so that I can, like, you know, respond to you. I need to see how you function. Anis say negative. In the dense sand, Anis, negative question mark. Hafizi blank. Muhammad no Hafizi blank. Sorry. Azli say yes, negative. Anis say positive now. Mana satu, Anis? Which one are you confident now? Negative or positive? Anis, which one? Negative or positive? Aha, don't know, sir. Ya Allah. Yeah, look again, everybody. At least now I know how to respond. You see? Tak apa. Here's my pile. See this? It's below my surface of the soil, right? Here's my surface. Here's a load. Load from the column going down here. All right? So this is my load. Okay. Einstein, not Einstein. Apa tu Newton said to you, for every action there is a reaction. Agree with me? Yes or no? For every action there is a reaction, right? Agree. Fazli say, okay, right. Makno pun sama juga. Ini pun okay. Now the load is in this direction. This is the action. My reaction is coming from the bottom, one at the tip. The other one around the shaft, which is the friction of the soil. So the tip is the easiest one. It has to be in this direction. Yes or no? Opposite to the load that I give. True? Yes. Okay. Friction is also has to go through the same way, the same direction. Yes or no? Same direction. Opposite to the action. Right? And let's check out yes. So in this direction is positive. Okay? All right. Fine. Now, look in the dense end. All right? Is it positive or negative now? In the direction I said to you. Oh, Anis now says positive. Fazli, are you saying positive? Okay. All right. Everybody says positive, right? You agree with me there. In that direction, it has to be positive. Now, in the soft clay, it's the opposite direction. This is not in the same direction now. Is it positive or negative in the clay? Because the soil is pulling it downwards in the clay. In the clay, is it positive or negative? Right. Okay. So put it in your head. That's the negative skin friction. That's why they say negative skin friction. Skin friction around the shaft. Okay. Around the shaft is negative. And then negative going downward. Right? Okay. Fine. So I've explained to you what is positive and negative and why, all right, it occurs because of the settlement. Right? Same story with that bridge apartment. You have soft clay, you have dense sand, then you put a fill. The fill is to, first you make the bridge. Then the fill is just to make the soil, all right, level with the bridge top, because that's the one. You're going in that direction, all right? The picture is like that, you're going in that direction. The car is going in that direction. So you fill up to the bridge side. I mean, to the surface of the bridge. Okay, here's the surface. Your car is going in that direction. This part here is the pavement, all right, where you walk. Human being walk here, car going this way, and car going that way. Okay? All right. You notice that this part here is inclined. It's inclined because at the bridge, as you move into, as your car get into the bridge, all right, you give it a sudden jolt. So you give also a negative, not a negative, a horizontal force to the soil. So you incline it so that you can resolve the forces in the horizontal direction, and you oppose the force that you give from the car. All right, that's additional knowledge. You don't have to remember that. All right, so you have this fill, it's subtle as well, because you have dissipation of excess for water pressure, additional stress. All right, so you get negative skin friction in the soft clay, not in a dense sand. It wants to pull it down. All right, that's why the arrow is downward. Okay. All right, so the phenomena has been explained to you, all right, and you know in which direction is negative. Now you can look at the bottom, and it says to you that the negative skin friction in end-bearing piles can occur due to consolidation of soft clay layer or silt or peat layer under weight of fill. I have explained to you, you put in the additional stress on the clay layer, it decides to settle because there is now new dissipation of excess for water pressure. Or the second part is settlement due to lowering of water table in normally consolidated or slightly over consolidated clay. All right, I've already explained what is normally consolidated and over consolidated previously to you of clay. All right. Just to remind, normally consolidated is that if you have layers upon layers upon layers upon layers being formed over a number of years and time, all right, then it's called normally consolidated. If you excavate them, all right, then the element of the soil underneath your excavation is now experiencing over consolidation. because it is now not being stressed. It's being relieved of the stress. So that's overconsolidation. Remolding of clay when pile installed. When you bang your pile in say clay, all right, the sudden banging, bang, right, increase the pore water pressure in the pores of the clay. That results in remolding of the clay. The clay becomes less strong, all right? Become less strong because there is an increase in pore water pressure, right? You suddenly go bang, pore pressure goes up immediately, then it comes down. So it becomes weak, all right, when you do that, all right? So the NSF, negative skin friction, it reduces the supporting capacity and increases the axial load in the shaft. Okay, you see this picture here? This one here? If this is, say, some clay that doesn't experience this field settlement, in other words, you don't get this direction of the shaft friction to be in the negative direction. Say that nothing happens to it, you put field, it is stiff clay, no settlement, all right? So the skin friction would still be positive, all right? Because no settlement pulling it down, so that it's positive. So positive, fight against the load that you apply. Now, we have positive here, you have negative here. Say you have 10 units of load you're giving. This is from the dense sand, you get 8 units. And from the, say you get from stiff clay, 2 units. Okay? But 8 plus 2, 10, fight against 10, okay, cancel. Now, if it is negative, all right, 10 going downward, you get 8 here. This minus 2, negative 2, 8 negative 2, you get 6. So it's lesser now. You see what is meant by that thing that says reduces the supporting capacity and increases the axial load in the shaft? Yes or no? That's why I was trying to explain to you positive, negative, and then counteracting the load that is given. Yes or no, guys? I need to say yes. Okay, fine. Adi says yes. Moaz says yeah. Okay. All right, fine, good. Now let me just take this water, drink it, and then let's go to example 8.7. All right, example 8.7 will reinforce some of these positive, negative ideas. I believe it's on page 347. Yeah. Example 8.7, page 347. Oh. Okay. We have a precast concrete pile, 450 millimeters square in section. So now you don't have it circular in shape, the pile. And it forms part of a jetty to be driven into a river bed, which consists of a depth of sand. The result of SPT in the sand are as follows. So in the sand, you either do SPT or you do CPT, very difficult to sample. So you have a certain depth, all right, here, depth 1.53, 4.5. So at about 1.5 meter depth, 1.5 meter difference, you get to do your SPT. Remind ourselves, SPT, you drill a hole, then you take all that bit that drill the hole, then you put your SPT inside, inside the rod, all right? You go down there, you go bang, 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 bang at 1.5 meter. Then you take it out, you advance the hole, then you take it out, then you put the SPT again, you put it in at 3 meter, bang, 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 bang. Okay? All right. So 1.5, 4, 3, 6, 4.5, 13, blah, 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 blah. All right. Now, the pile is required to support a compressive load of 650 kilonewton. So, here's my pile, 650 from the top, compressive. All right, compressive. All right. And to withstand an uplift load of 225 kilonewton. Wow. The load factor in each case is to be at least 2.5. You need to determine the depth to which the pile must be driven. So I'm going to have this pile, and it's going to be a part of a jetty, like a bridge. Bridge. And it's going to be on a river bed. This is the river, the surface of the river. All right, water. Okay. So that's why there is an uplift load. Why is this uplift load? Because this river is nearby a sea, and the sea has tidal changes. So some of that water sometimes goes down, some of that water goes up. High tide, low tide. All right. So you're going to have some of that water going upwards in the sand. And this is going to result in uplift force. Uplift force, here's my pile, here's my surface of soil. Uplift force is going to push my pile upwards. See, my pile is not going out of the sand. Okay, guys? That's the uplift force. Okay. So, I want to ask you now the direction of that uplift force. Is it positive or negative? In which direction? Positive or negative? Muaz says positive. Good for you, Muaz. So, positive direction, right? But now, this positive direction, you don't want this positive to be a part of your, well, it is not a part of the soil, right? In terms of the bearing capacity. It is a part that is going to push my pile outwards. I don't want that. You want that? You don't want that, right? You want your pile to be taking care of the load given to you, right? So I need you to have this idea, and then for now, so that you can see why they are doing all these calculations later on. So the ultimate compressive load is just the tip of the pile multiplied by the ultimate bearing capacity plus the shaft friction multiplied by the skin friction. They said to you that the load that it must be applied is 650. So you multiply by the factor of safety, minimum that you need is 1625 kilonewton. All right. And then it says the uplift load. On top of that, this pile now, first, the load that is given from the soil, you get 1625, which must counter this column load that is given. Then there is this uplift load, which is going to push my pile out. So they say ASFS, the skin friction now must counter that uplift load. So 2.5 is the factor of safety, multiply 225. Okay, you get 563 kilonewton. Now, A sub B is 0.45 squared, all right? It's given to you, 0.45 meter squared, meter, right? You square the 0.45 meter, then you get the area. And A sub S is the area around the circular perimeter, not circular, the square, the perimeter of the square. So 4 times 0.45 multiplied by the depth of the pile friction. Right, the shaft friction of the depth of the pile. All right. So now, if you look over on the next table, page 348, and if you use Mayhof correlation, all right, use Mayhof correlation, which we had that used before initially on page 336. All right. Q sub F is equal to 40 multiplied by N dB, which is at the base, diameter at the base, divided by big B, which is the diameter of the pile. It must, however, be less than 400 N. Okay, must be less than or equal to 400 N. So it's the tip of the pile, the tip resistance Q sub F. Then the skin friction on page 336. All right, this is Mayhof empirical using SPT. All right, is equal to 2 N bar, kilonewton per meter squared. So now the calculations are set in table 8.9 using these two. So this is the depth of the base, 1.5, 3, 4.5, 6, 7.5, blah, blah, blah. Okay. Then the SPT, you just take it from earlier, 4, 6, 13. Then N bar, okay, 4 plus 4, the first one is 4. All right, N bar, there is no average, same one. Then you have 6 at 3 meter, 4 plus 6 divided by 2 is equal to 5. Then the 4.5, 4 plus 6 is 10 plus 13 is 23. 23 divided by 3 is equal to by maybe 7.5. 23 divided by 3 berapa? Ain? I'm waiting for Ain to answer. 4 plus 6 is 10 plus 13 is 23. 23 divided by 3 average. Berapa? Fazli say 7.6. Ain tak dapat lagi cari calculator. So why can't we put M bar 7.6, Fazli? Why does he put 8 instead? I've explained this before to you guys. Sebab tak ada 0.6. Apa yang tak ada 0.6? Akbar kata tu sebab tak ada. Mana ada ORG PAS 76 kali. Pasal? Itu tak cakap apa. Kena cakap betul-betul lah. Genap kan? Pasal apa? 8 je kenapa? Pasal dia bang. Berapa? 1. Bang. 2. Bang. 3. Mana ada 36? Ada. Bang. Ada 26. Itulah kena cakap macam tu. Sasha, Andy pun. Bang, bang, boom. Boom berapa? Boom 2 kali. Bang, bang, 0.5. Okay. That's why there is no 7.6. There is 7. There is 8. Okay. So just to remind you on all of these things again, we have learned this before. You know, some of you tend to forget it. Now we want to find the skin friction. So A sub S multiplied by A sub S. So you get for the first one 222, 4 times 0.45, multiply D sub B, which is 1.5, multiplied by 2 N bar. All right, 2 N bar. N bar is equal to 4. So you get 22. All right, you can calculate that yourself. And then you use Mayhof. The first row of Mayhof is 40 Q sub F. This is the tip resistance. All right. 40 divided by 0.45 and D sub B. So the first one you get 535 must be less than 400 N or equal to 400 N. If it is less than 400 N, you use that one. If it is not, then you have to use 400 N. So 40 divided by 0.45 and D sub B cannot be more than 400 N. That's why you have 2 columns there, and then that's why they don't bother to calculate beyond 5,200. Because at 5,200 at 4.5 meter deep, the 400 N value is already 5,200. And there is a limitation according to Mayhof, it has to be less than 400 N. Okay? Okay. Next column. So you calculate A, B, Q sub F using the values that that you just calculate. For the first one is 0.45. Yeah, AB multiplied by Q sub U or Q sub F. 535 multiplied by A sub B. All right. A sub B is the diameter you already know just now. You calculate a few minutes ago. So 0.45 multiplied by 535, you get 108. And then the shaft friction, you add that up to this shaft friction, ASFS, and you get 130. So you calculate all of those columns. All right, and except for the 1, 2, 3, 4, 5, the fifth column, you don't bother anymore beyond 5,200 because 5,200 is the limiting value of the 400 N. Above that is 100, you don't bother. All right, okay. So you know how to do all those columns. Now, what is it that we are trying to do? That's being referred to in the next paragraph. It says, by inspection, uplift is the limiting consideration. By interpolation, the pile must be driven to be at least 10.2 meter. The load factor under compressive load is 10, 3225 divided by 650 equal to 5. Now, this business just now, a few minutes ago, you take over the, if you refer to the previous page. All right. You remember we said the ultimate compressive load, all right, is 1625 kilonewton. I'm on page 347. The ultimate uplift load, 2.5, right, is 563 kilonewton, right? So if you look at this here, right, AB plus ASFS, you notice that, you know, above 1625, there is no problem. You know, you can take that 1625 up right up to 9 meters, right? Right up to 9 meters, you see that it's already 2365, the total load. So you can take the skin friction, the skin friction and the, sorry, not the skin friction, the compressive load of 650 kilonewton multiplied by 2.5, because it's already 2365 at 9 meters. Yeah. But the problem is this uplift load of 563 kilonewton. You see, this uplift load of 563 kilonewton, it says here, uplift is the limiting concentration. By interpolation, the pile must be driven to at least 10.2 meters. Remember I said to you, at 9 meters, the total value of the ABQF plus AS up F sub S is already 2365. So I don't have problem to take care of, what was it? 1625 kilonewton of ultimate compressive load. But at that point in time, at 9 meters, you notice that ASFS, the skin friction, is only 421. But I have an uplift load, which is 563. So 421 is in this direction. Yeah, going downwards in this direction. But the uplift load of 625, of 563 is in this direction. Uplift is pushing my pile out. Right now, I talk to you about shaft friction. This is a negative shaft which must oppose my uplift load. Here, the negative value is in this direction. It's okay. Why? Because I have this uplift load. So they cancel out each other. The uplift load is, again, 563. So between 9 meter and 10.5 meter, 421, 9 meter, 10.5, 605. So if I interpolate, I will get this value of 10.2 meter, which is going to be equal to 563 kilonewton of the shaft friction of the pile in this direction. It's going to cancel my uplift load from the water. Okay or not okay, guys? The shell says okay, but this is okay. That's why the direction now becomes important. A few minutes ago, I said about negative skin friction, right? But here now, it's in a negative direction, but it has to oppose the uplift load. All right. So that's why it's a good negative skin friction, if you like. Right. So don't put it in your head that negative skin friction is always wrong. It's always not good. So then load factor under compressive load is then 303,225. At that 10.2, you will interpolate the value, you get 303,225. Compressive load is 650. Now the factor of safety you get is 5.0. See, you only need 2.5. Right? A few minutes ago, you calculate, you say, okay, minimum 2.5. 2.5 times 650, you say 1625 kilonewton. Now, because you want to take care of that uplift load, your factor of safety now has increased to 5. Only because of that uplift load. All right? If there is none of this uplift load, you probably don't have to have a factor of safety of 5.0. Right? Okay, good. Now I'm on page, next page, all this geology stuff. I'm done with all the calculation. Right? Okay. So, we started off trying to find the bearing capacity of pile. right, of a single pile. And we said to ourselves whether it is in clay or in sand. If it is in sand, you can use the SPT and CPT. All right. And then in clay, you have all these formulas. So you said to yourself there are three methods by which you would be able to determine the ultimate bearing capacity and therefore the allowable bearing capacity of a pile, whether it is single pile or in a group. All right. So the first one was a pile load test. All right. The second one you say using the static load formula. The third one is what was the third one? Use a dynamic formula. In other words, you bang it in. This only work if you bang it in. You install the pile using those dynamic method. Right? If you use a board pile where you just drill a hole and you put reinforcement and then you pour concrete into the hole, then you cannot use it. All right. So those three methods. So and we said to ourselves, because pile load tests are expensive, maybe you can use only 3%, right, of the pile to obtain your ultimate value. So you need only to use the static formula because this is expensive, right? The pile driving test also the same thing, not the pile driving test. The pile driving formula, you also use it to confirm your static formula prediction, all right? Then you, generally speaking, piles do not have problem in terms of settlement, right? Occasionally they have settlement problem. So that's why you need to know how to measure the settlement. And the settlement is the one in clay is you use the equivalent method where you say the pile load is acting at an equivalent rough at 2/3 depth with that stress transmission. All right. So then you calculate the settlement using the Scranton barrier method. If it is in sand, then you just use empirical formula, right? Rho one and all of that. All right. So done. We know how to predict the ultimate bearing capacity using all the theories. Now the question is it okay for me to install the pile? That's when you need to have an understanding of the geology and the site investigation again. All right. So on this page, I'm looking at figure 2. All right. Figure 2 says Geological Map of Peninsular Malaysia. This is your Dr. Dane stuff, Dr. Zainuddin. When I think you saw him in what? In the first year, second semester perhaps. Am I right? Or is it fourth semester? Akmal says yes. Yes meaning what? Second sem. All right. First year. Okay. Just reminding you again. If you look at figure 2, all right, you did all this mineral identification, rock, good. Mineral identification, rock identification. Then you had do you have a geology camp or you just went to Cameron Highland? Fazli says Mosque. Oh my God, I remember. You went to Cameron Highland on a camping trip or you went to Cameron Highland on just a field trip? Because right now, nowadays, with all the COVID and everything, they don't have any more all this. Field trip. Oh, okay. Bukan apa tu surveying camp, like surveying camp. You have geology camp, you have surveying camp. Field trip only, okay. You see a lot of us, you know, who went to do civil engineering. I did the same with you. All right? Okay, good. You went surveying as well. 2 in 1, yes. Normally they are 2 in 1, correct. What am I trying to say is that when I did my first degree, you know, it's overseas, of course, and then there were many universities in Malaysia then. So we went into the mountains. So, you know, we went into the mountains and we stayed at some hotel. So it was like 1 week, all right? 1 week of surveying and geology camp, that kind of thing, all right? So a lot of the time when you talk to people my age, or maybe even you people among yourself, when you have finished your degree and you are working, the thing you remember most is your geology camp, your surveying camp. You don't remember all the formulas, but you remember the camp, all right? Because it's something outside of your class, you know, you stay somewhere else. So Akmal is saying true. Good. you will see that in your future life, you will only remember it. All right. And perhaps you remember your lecturers, and especially your lecturers who are the one who are strict, the one who give you a hard time. You will remember them. The other ones you don't remember because they are too nice. You forget. Okay. Anyway, geological map of Peninsula Malaysia. I'm going to go through this quickly just to remind you. All right. You see on that page of Peninsula Malaysia, all right, there are all these residual granite soil, sedimentary rock soil, coastal or river alluvium, and limestone facies. The coastal or river alluvium are along the beach, all right, along the beach, along the sea, the coastal side. The granite soil is along the mountain range of Peninsula Malaysia. I'm just reminding you about Peninsula Malaysia only. I'm not talking about East Malaysia and all of that. I think that one Zainuddin would have told you about it. I'm just trying to relate to you why geology and site investigation is important for us to install the piles. All right. So along the mountain range, the one that we call the one that we call Banjaran Titiwangsa. All right, Banjaran Titiwangsa is the main range. For Moaz, it's called main range. If you've been to Cameron Highlands, Moaz, as in his weighing camp, all of this field trip, then that is part of the mountain range, which we call Banjaran Titiwangsa, or in English, it's called the main range. All right. That is correct, Fazli. Yes, I did that University of Wales in Cardiff, but you know what? That university doesn't exist anymore. In name, the buildings exist, but in name, it doesn't exist anymore. They have a new name now. Okay? See, the world changes, you see. One university buy another university, and then it become, some university don't have students, some university lose money, they don't do research, so another university grab the other university, and form another university. It's now called, by the time Dr. Nick went to the place I went, it's already called University of Cardiff. All right. Anyway, that's another story. I will talk to you about it later. So, mountain range, main range, you have granite. But and then this beside the mountain, you have the sedimentary rock soil. All right. And then in places like Ipoh and in the Klang Valley, where they mine tin. Long time ago, Malaysia made our money from tin mining, right? Not from oil, from tin mining, which now you don't have that industry anymore, right? Tin mining. You have all these ponds, like the pond, that lake or pond in front of the Faculty of Engineering, right? If you still remember them, right? The pond. That is a remnant of tin mining. See, they mine the tin and then they take the soil out and put it on beside the pond, and then you have new field, and then it becomes a pond after that, after finishing with the tin. All right. So you notice a lot of these ponds occur in the Klang Valley around Kuala Lumpur, and also in Ipoh, right? Many of these people, and then some of these other places. These are limestone, all right, limestone areas. And on top of the Peninsula Malaysia map, all right, is figure 1. Now, that is a geological evolution of a limestone rock, okay? So A is the limestone when it is young, right? When it's young. So this is happening as you and I are living. Of course, the process of A, B, C, D takes a longer time. We probably dead by the time some of those limestone become D, right? But at this stage of our life, some limestone are A, some limestone are B, some limestone are at stage C, some are at stage D. All right. So some just when we die, we probably don't, some of the limestone are probably not even D yet. All right. So I want to convey to you the message that limestone are a living thing. All right. And they are being eroded with time. Okay, so A is when they are young, youth, right? Okay, and you just have all this block of limestone, and then it is cracking up. All right, the block of limestone is cracking up, and it cracks up because of your atmosphere has carbon dioxide, and then it has rain. Carbon dioxide mixed with rain becomes carbonic acid. All right, becomes carbonic acid. Now your teeth is made of calcium. All right, this teeth made of calcium. Limestone is also made of calcium carbonate to be exact. If you don't brush your teeth at night, at least 2 times a day minimum, all right, and you keep not brushing your teeth at night, right? The teeth will corrode because you have all this food lodged, right? Yeah, food lodged in your mouth. Then there is bacteria. You have good bacteria, you have bad bacteria, right? So some of that bacteria is bad, some of that is good. But anyway, the bacteria, all right, feed on those on those food waste that you have in your mouth because you haven't brushed your teeth, and then they give off this acid, right? The same acid that is acting on the calcium carbonate, the limestone oxide. So that's why your teeth, right? It corrodes, it gives you a big hole in your teeth, right? It gives you a gap, and then you have to go to the dentist, and the dentist has to fill it up with cement, all right? If you keep doing this forever, then by 30, you probably don't have teeth anymore. Lose your teeth, all right? So why am I talking about teeth? That's the same eroding process that is going out there with respect to limestone. So you have all this slot, all right, and cavities are being formed, all right. So the word C in A is cavity, and you have this slot, right? This carbonic acid, right? They flow through the limestone, and then it erodes the limestone, right? Corrode limestone, and then you get a cavity. So that is when they are young, that is happening. And then B is when they are slowly becoming maturity. So young is, teenager. Early maturity is like about your age, say, 21, that kind of thing. So you see that all this corrosion and erosion is happening, which results in the cavities, C, and then you also, some of those cavities, the erosion of the limestone from rock, right? Limestone is actually soft rock, right? So the soft rock, then it erodes to become soil, okay, residual soil, and then it falls into the cavity. Cavity are just holes, right? It falls into a hole. That results in a hole on the surface, which we call sinkhole. You notice this sinkhole a lot of the time occur in Ipoh. Anyone from Ipoh? Nobody from Ipoh. All right. So you can have a nice house, and then suddenly you have a sinkhole beside your house. All right. Big sinkhole. Or if you are unlucky, your house falls into the hole. A lot of that occurs also in Florida, in the United States. Okay, because they have the same setup of limestone. See, more erosion, you get residual soil. Residual soil, by the way, is a soil that is being formed, right, being weathered at the same place, in situ, as unlike transported soil. Transported soil is like your till. You remember your glacial till, your test one? You get snow, you get ice, and then you get melting of the ice, all right? And then it erodes the rock around it, bring that rocks and boulder and soil, all right, all the way through to some other places on earth, and then it deposited them. That's transported soil. Okay, transported soil. Now, residual soil, transported soil. So you get C. C, you have R, the residual soil. P is a pinnacle. Some of those rocks that are constantly being eroded. Some of it is being left jutting out of the soil. All right, it's like a pinnacle, right? Like a chimney out of the soil. And then you have this overhang pinnacle, right? Overhang pinnacle. It's like a cantilever, right? Cantilever. But you notice that among the limestone, you have cracks occurring as well. So if you have that overhang and you sit on that overhang, which is like a cantilever, and it has crack, you might just fall over, right? The crack it might just break off from the pinnacle. Right? So you have soil and you have residual soil and you have rock and all that. And D, finally, all of that limestone is almost finishing. All right. You have some of those blocks remaining, but generally they are becoming all this residual soil. And then at the bottom there is it's just the sandstone. That's the stone which resulted in erosion that finally will become sand. All right. Okay. So the idea is that you can have this happening to limestone. All right. Now, I want to look at the limestone part first. Then I'll go back to this schematic of Kuala Lumpur, right? So let me go to, because we are talking about limestone. Let's look at this first, this limestone. Are you on limestone now? Okay. So I'm on figure 4A. Because, you know, I can have this limestone where I can now have this karstic formation. Karstic formation is like on that figure 4A. Right? It's at the it's at the stage C, which is late maturity of the limestone. All right. So I can have a cliff, I can have that overhang and pinnacle. All right, the overhanging is the overhanging from the pinnacle or from the, well, from block of rock, of limestone rock. And I can have cavities, all right? And the cavities, like I said earlier, can be collapsing, and then the soil can go into the cavity, I can get a sinkhole. So all of that is happening, right? And this is important for us to realize that this is happening because we are building our building, we're constructing our building, we're putting it on our limestone. Kuala Lumpur is on limestone, all right? And this is happening. So you imagine you put all your pile and then, you know, this is happening. So there could be a cavity, which is why you always guarantee your building for only 50 years. Beyond 50 years, you say good luck to you, right? Anyway, you get that? 50 years. But you and I live beyond 50 years. And you and I live in a building more than 50 years sometimes. Right? Like I am, you know, well, not in this house. This house is relatively new. Yeah. You may get your house from your parents, all right? And they've been living there for 30 years. And then you probably live in that house again for another, I don't know, 60 years. Then you are living in that house for 110 years. It's definitely beyond the guaranteed life of the building, especially if you do not maintain it and if you don't, you know, check for how it is functioning. Very few people check their house beyond 50 years. They just assume that their house will be there forever, which is not the design life of that building. Okay, guys? So anyway, you look at piling problem in limestone areas. Now, in the one here, cliff, it's R-shaped like that. You're thinking of putting your pile straight down, right? Because you're thinking of having a bearing capacity type of pile, the one that obtain the ultimate bearing capacity from the tip. All right. And what instead happens is that it goes through this cliff and it come out here. That's not what you want, right? Is that what you want from your pile? Definitely no, right? Okay. So then on the overhang, on that overhang, like I said, you know, you have cracks there. See, I have a crack there, and you keep banging on it because you're thinking again that you're going to have your pile being supported by a rock type of material. And what happens if you keep banging, there is a crack there, and then it will just fall off one day. Because soon this pile, you are applying load to it. You're going to have your column load, and then you're transferring all that column load to that pile, no? See? And then here, again, instead of you, right, you're back, you get to this stage where you install the pile, you bang the pile in, and then it hits a cliff side, right? The cliff side, and then this pinnacle side, all right, and it follows the inclination of that limestone rock, right? And again, you're having at a inclined shape, right? Which you don't want. You wanted initially to be straight like that, all right? Unless you design it to be inclined, because to take horizontal forces. In this case, it's not, right? So it's the same here, right? Same here, and then this, because it is along that inclination of the slope, so it is not going to be staying still, all right? Because it's going to be rotating, right? And then you have that sinkhole. So the solution is this one here. What you do is that you put some small diameter piles, which we call micro pile, and then you bond it. You drill a hole in the solid limestone rock, all right? And then you bond it, you put glue onto it, and then you drill a hole, excavate a hole, and you put reinforcement. Then you pour your concrete, your board pile. So you have your board pile being attached to a micro pile, being bonded to the solid rock. All right, that's the solution. Otherwise, you get all this problem. By the way, that KLCC building, that Twin Tower, it wasn't supposed, if I recall, I don't know whether I've said it to you, but I think I did at some point in time. Anyway, just to remind you, it wasn't supposed to be at that corner. The corner now I'm talking about is now located on the corner of Jalan Piramli and Jalan Ampang. It was supposed to be Jalan Piramli and the other road here. Well, I don't know what that road is called. I think it's called Jalan Piramli. Right? Now that Jalan Piramli becomes like that and comes like this. So it's supposed to be there. But because, it was such a tall building, lot of load being applied, and you have this situation here at that corner. Right? So they decided that no, we are not going to take the risk. We're going to move it to the other corner. Through the site investigation, they find that the other corner, the current corner, the present corner, is more stable. All right. So that's the story of Twin Tower. All right. Anyway, any questions on that? Now you see why you need to learn geology and why it's important to understand that limestone is being eroded, because it has an impact on what you do in terms of your foundation. Yes? Nobody is answering me. Yes. Okay, good. It's not that I am correct or I'm not correct. Okay, what is important is for you to realize why you need to study certain things. Because as a student, right, sometimes it's boring to learn geology. Let me tell you this, right? Because, fine, I have to know what a granite is. I got to know what I have to memorize. It's not like doing your calculation, right? Okay, most of you who like to do calculation, you don't like to memorize things. Okay, most of us are like that. That's why we do engineering, all right? So that in a class like geology, you have to memorize things. You have to memorize what granite look like, what limestone look like. It's always easy to identify granite. It's always easy to identify limestone. But the others, when it's shale, sheets, you get a headache, right? So we all have to learn that. And then for me anyway, I had to go to field trip. We had to go and identify the rock. You had to put the stereoscopic. I don't know whether you do it. The stereoscopic plot, and then we have to plot it. you know. So it's interesting. But when you go to an exam and you have to memorize things, you are a bit tired. Yeah, because a lot of writing is involved. Okay. So sometimes, right, we get tired and we sleep in the class. All right. So one of those things. Okay. So I'm just trying to relate to you why sometimes we have to go through the border of learning certain things. All right. The border of learning certain things, and then, you know, how it impinges and how it impacts us in real life when we work as an engineer. So I'm not an expert on geology. Dr. Dane is an expert in geology. So, you know, I have to understand the geologist when he explained to me all this geology stuff. See, if I don't do geology, I don't know what he's talking about. See, that's why you learn geology. All right? Okay. Now, next is this. You see this picture here? This is what from the Peninsula Malaysia just now. This is a magnification of the Klang Valley. In particular, it's a schematic of the cross-section of the rocks, of KL. So you see that you have this Kuas Dike. The Kuas Dike is in Ulu Klang, right? Ulu Klang area, Ampang area. Now, to give you an indication of this schematic, the Canning Hill Formation is where the Parliament is, that area, right? And then you have this schist. Schist is if the Kuas base, all right, is the the Kuas Dike is Ulu Klang area. So that's not southeast, the eastern side of Kuala Lumpur. So this Kuas mica schist is on the western side, and in between there you have Parliament, right? Canning Hill Formation. They call it Canning Hill because there is a hill there which one of these colonial officers used to live there. His name is Kenny. He found out about it. All right. So underneath there you have schist, then you have Kuala Lumpur limestone, the limestone that I just talked about it a few minutes ago. Then underneath it you have this schist. All right. And in between that Kuas Dike, you have that granite, which is the mountain, which is near that granite is the Genting Island. All right. You know where Genting Island is. All right. Just to give you the geology of this area. So the cross section is given here. All right. I'm not going to bother explaining this. You have your geology. Having that in mind of the Kuala Lumpur area of the limestone and whatnot. So you have this one here, sedimentary rock. Yeah. If you are in the Kuala Lumpur area, you have to deal with all these things. So apart from the limestone, you may have this Pickle 4B, which is in the sedimentary rock. You have that laminated shale. The shale, it tends to erode with time and at an inclination. See here, the inclination here? So you have the pile and you drive the pile and then it wants to go that way along the alignment of the laminated shale. And then for the second one here, it says low bearing. You thought that you have solid rock, but it's not solid rock because it has been crushed with time and erosion. So, you know, because when you do your SPT, you say that I hit rock. All right, if I have my SPT more than 50, then I'm okay. Well, you may not be hitting solid rock. You may be hitting something like a weathered rock. And then this oxidized limestone is just a big boulder in the soil. So again, you believe that it is solid rock, but it is not. All right, it's just a boulder in the soil. And then if you pile and it hits the sides of that rock, it's going to be bent, and then your pile is no longer performing well. You remember one of the three criteria for a pile. Okay, the bearing capacity you need to satisfy. The settlement you need to satisfy. This is correct for all foundation. But with respect to piles, there is additional. You say that the material that you use for the pile, whether it's timber, steel, or concrete, it shouldn't be overstressed. You shouldn't overstress it. If you overstress it, the material used for the pile is no longer workable. It's not performing anymore, right? It cracks, and then it's not a structural. Structurally, it's not integral anymore, right? Your structural integrity is now questionable. Then the last part here is the one that occurs all these boulders, right? All the solid rock, they are weathering, and then you have all of this, right? So here in the granite, the one in the granite, it is inclined bedrock, same story as the laminated shale. Then in between here, you have these two rocks, right? So you are actually driving the paths in between them. They are subjected to this wall stone, right? And you have these high bending stresses in between, all right? Now, finally, you have alluvium. The alluvium is in places like Pelabuhan Kelang, Muar, all right, in Johor, all right? They have clay, lots of clay. So you have all these problems of negative friction. You know what that is. You put the field, then the friction is going to pull it down. These localized sand lances, you know, sand in clay. The sand, you know, you have water in the sand, right? But it cannot go up. Why? Because the clay is surrounding it. Because the clay permeability is lower than the sand, right? So now you have pore pressure in sand, all right? Because it cannot be dissipated. So the sand lances, this has much less strength than clay, all right? Now this tensile stress wave, so one part of the clay of the pile is in the sand, the other part is in the clay. They have two different strengths. So as you bang it, this side here is pulling it down, the other one is pulling it up, because they have two different strengths, right? One has 50 units, the other one has 100 units. So there is an overbalance when you pile them up. So what will happen is that you break the pile, okay? It's like my hand here. This is being pulled down, this is being pulled up. In the end, I'll just break into two, right? If you keep doing it. Then same story here, this directional instability. All right, same story, directional instability as with respect to the rock. Okay, and then in these three things here, I need to explain. Just first, you pile in the middle, right? Pile in the middle. Then you do another pile here, right? And you're suffering from that upward and downwards stresses. Okay, and then the third one, you pile here. Okay, I don't have another pile here. All right, here I am. I have another one here, and then I have it, parts of it in sand, parts of it in clay. So some of it is going down, some of it is going up. All right. So while I'm doing that, if I bang it in, this one will go up. So it's like a trampoline. So that's what the picture is trying to say. And then the last one here, high lateral load. The high lateral load, right? You have you have this big equipment that you want to bang the pile in, all right, hammer the pile in. But what happens is that load, because it's moving on a soft clay, all right, we transfer the vertical load, goes down into the clay, it becomes a horizontal load, it transfers the source, so now your pile is walking, all right? It's going walking like that. So I've seen it on site, it's walking. So some of those people who do not understand soil mechanics, they get worried. They say there is a ghost or a hantu in the field. And then tomorrow, some of them, they decide to slaughter goat, right, to appease the ghost. All right. So you see some of this in the construction site. Maybe these days you don't see many of that anymore because nobody, no, people are not afraid of ghosts anymore. They don't care anymore. They say, oh, hi, ghost. You know, don't come bother me. Very rarely that first day. Not many people are afraid of ghosts anymore. In fact, if they see a ghost, they ask for money from the ghost. They are afraid of COVID. Disease is right. Okay, guys. So all of this thing about the installation is given in the set of notes. I assume you're going to read this, right? Because otherwise I could just read it to you, but you know, it's been very boring. So 8.2 residual soil, 8.3 soft alluvial soil, and those are the two topics I believe. 8.1 is where is 8.1? 8.1 is limestone formation. Those are things that are covered in all those pictures. All right, so you'll do the reading. Okay. Right, guys. I think that's the end of today's lectures. I'm done with files. Right, I'm done with everything, and this is the last class. Homework I was going to ask from you too, right? 1410 and 810, right? Whatever it was. Yes. So I think we need break. No, Fazli, we won't have a break because we will finish quick. It's 4 o'clock now. Lepas tu, I've already finished with class. Iza, yeah. Ni apa benda? Wahaha ni apa? Alright. So, lepas tu menyembang. Yeah. So now I have a few things to finish up here. Alright. Okay, I finished. And homework. What was it that I asked from you yesterday in Putra Blast? 810? Hey! Okay, Iza says 810. I have 54 people. If I'm nasty, I'm going to ask for another, I'm going to ask for the other homework to be submitted within 15 minutes. Should I do that or not? Ni apa benda Rohimah tu tayi buah ni? Jap sir, nak kena type lambat sikit. Apa benda? Type apa? Okay, Anfitra 810. Okay. Alright. That was the question, 810. So, the other one is what? I haven't asked from it, right? 14 point something, 1410. Okay. Now I have 53 people. Arman, do I have 53 people? 52 people? Or do I have 58 people? Fazli says 52. Tu kat sini, Google. 54 dah pula. 53. Form says 58. Okay lah, kalau form says 58, tak payahlah. Alright. Because I think connectivity problem kot. I don't want to think bad of people. Okay. So submit just that 810 kan semalam on Putra Blast. Okay. Okay lah, whatever kan. So submit that. In fact, I gave a lot of time. I gave sampai pukul 6 petang. I gave to you to submit until 6 o'clock. After that, you won't accept anymore your homework on Putra Blast, right?